Good evening all. See, in the last class we studied about the attenuation and we see some of the important formulas for unit length. There is alpha attenuation is equal to P in by P out, and such alpha value that is also given as dV per kilometer 10 by L into log of P in by P out of base 10 dV per kilometer, and we study the P out output power. P out is equal to P L into 10 to the power of minus alpha L divided by 10 in terms of watts. So, when input power is given, attenuation is given, from that we need to calculate what the output power present, and such output power will be calculated by using the P out formula. And today's session we are discussing about the causes for attenuation. Already explained to you in the last class what are the different causes for attenuation we are having. So, I can start explain once again about the causes for attenuation, and we will see about the attenuation characteristics, and we also study about the components of optical communication system, and we can complete the session with numericals also. Okay. So, I can start explaining you about the today's topic with causes for attenuation. Present as causes for attenuation. If you see the first one, causes for attenuation, the first one is called as absorption loss we are having. The second one is called as scattering loss. The third important loss we have, which is said to be called as the waveguide bend loss. Your waveguide bend loss is also called as radiative loss. Is also called as radiative loss we are having. Fourth point, it is called as core and clad loss. Fifth point, that is the dispersion, which is the reason for having the loss. Sixth one is coupling loss. It's called as coupling loss we are having. So, these are the reasons for having the attenuation, causes for attenuation in optical communication system. So, yesterday's class I explained about the first low loss window, second low loss window and third low loss window. So, that advancements or achievements that we done in the first low loss window is nothing but an laser is fabricated at 850 nanometers, and the achievement that we seen in the your lambda 1300 nanometers is nothing but an it is fiber dispersion shifted fibers. Today's class I will explain that part to you, why it is called dispersion shifted fibers. And the third important one that we can see is nothing but an it is called as your WDM, wavelength division multiplexing technique. So, implementing WDM technique by transmitting the information from one point to the another point at 15 nanometers. So, amount of loss offered by the copper cable is 20 dB per kilometer. Amount of loss offered by the OFC optical fiber cable is nothing but an it is equal to 0.2 dB per kilometer. I hope you already wrote this point in the yesterday's class. So, in yesterday's class we stop our explanation at modern telecommunication uses 193.1 terahertz at 1552 nanometers. I hope everybody has recalled the entire concept. I think you studied the concepts. So, you revised the concepts. So, Bhaiya, what is the loss offered by the copper? Nana? Loss offered by the copper is, that is copper cable is nothing but an 20 dB per kilometer. It is equal to 20 dB per kilometer we are having. And next one is that is nothing but an OFC optical fiber cable is given a loss of 0.2 dB per kilometer is the loss we are having. It gives a loss of 0.2 dB per kilometer we are having. So, this is said to be called as the loss that is obtained. One is called as the copper cable. So high loss is getting 20 dB per kilometer, other one is OFC 0.2 dB per kilometer we are getting, very less low loss. Okay, please copy it. Very good morning to Radhika, good morning to Soumya, good morning to Sagar. Good evening, not good morning. Okay, very good evening. Right, I can explain you about the next topic, that is called as absorption loss. Please see here, absorption loss. I am explaining about the causes for attenuation. All of you concentrate. So, writing about the loss which is said to be called as absorption loss. Dear students, absorption loss. If you talk about the absorption loss, the first important point that I want to tell to you here is, before going to explaining you this absorption loss, I will tell you two important things. Please see how the fiber is manufactured and how you convert your silica into a glass, and after that we use the same concept in explaining of your absorption loss. ठीक है भैया? So just concentrate भैया, 2 minute concentrate करो all of you. Silica is nothing but a sand plus water. Silica plus water both are going to be added. So when you add both the silica and water both are added. They placed in a crucible pot. It's a crucible pot. Okay, in a crucible pot we are placing it. In a crucible pot, what we are doing is we are having the sand or silica. Some of the metals are present here like lead, copper, magnesium, okay, bauxite, and such type of metals are there. Such type of metals are present in the silica, right? And that is now mixed with water. So पानी से डालिया इसमें, so थोड़ा तक soak किया, and you can find out some of the dust particles that are present like some waste dust, wood or anything dust is present, it will come outside, that is come on the top of the water. You are going to remove that dust, everything clearly water, and again remove that water and again pour the water neatly into that one. So after pouring water neatly into that one, like this you can perform 2 to 3 washes, you are done. So after doing the washes, we are going to be removing off the complete sand. It is going to be obtained as the dust particles are removed off from the solution. So what is the solution? The solution is right now silica plus water without having any dust. Now you start heating this crucible pot. So up to by 1000 degrees centigrade, 1000 degrees centigrade to up to 1500 degrees centigrade we are completely heating it. So once you are heating that solution, which is silica plus water, of course washed silica plus water. So of washed silica plus water is completely heating of at 1000 degrees centigrade to 1500 degrees centigrade. What happened is this complete solid state of your silica is converted into the liquid or converted into the molten state. You convert it into the molten state. So we have converted that into the molten states. So that is the molten form we are having. That molten form is placed like this. It's a jar we are having. So molten state is placed like this. Say simple jar we are having, and in this one you are going to be placing this so the molten liquid is to be placed here. When the molten liquid is placed and you are going to be using the fibers to roll this one. So the fiber is going to be rolling. See, the rollers are used to roll the fiber. So we are getting a fiber. See, the fiber is having from the molten liquid, fiber is rolling, and you are doping some of the impurities. By doping the impurities, what happened? We are going to be forming the claddy. Doping the impurities, we form the clad, and by rolling, the fiber is going to be formed a length of 10 kilometers or length of 10, length of 20 kilometers, and of course higher lengths are also possible, but we can restrict up to 20 kilometers of length for the fiber. So like this, it is going to be having the 20 kilometers of length of fiber is to be manufactured in this technique, and after that you can give some buffer coating and you can add some kelver, and after that outer jacket is placed, then the fiber manufacturing is completed. So this is the process of how the optical fiber cable is manufactured, and that optical fiber cable which is manufactured has to be done in this way, such that you are having the process of making the fiber, and that is going to be giving a length of the fiber. Now explaining you about the absorption loss. So how much length you wanted, that much length you are going to be designed, but not up to 1000 kilometers of distance, because this is not supported by the manufacturing plants. So 20 kilometers, 30 kilometers also support, but maximum 20 kilometers they can have it. More the size, what happened means the difficulty in making a bundling and carrying is also become difficult by the size of the bundle is very, very high. So that's why what they do means they restrict to 10-20 kilometers of size only. Okay. Yeah, now see here. After this, once you see about the absorption loss, so try to understand the absorption loss we are having. Absorption loss is the loss which was going to be obtained by the impurities that are present in the your fiber. What is the main source of these impurities? Because earth was going to be, silica was going to be having some impurities, and those impurities are metal elements are present. The metal elements are going to be absorb some light. So due to this reason, what happens means we are having some absorption done for the optical light, such that it creates a problem, and to rectify this, what we are doing is make the impurities to be less in the silica while manufacturing, and also make sure such that it must not be having more amount of ions to be present. So please see the concept. I will explain those points as a note to you. So absorption loss, absorption loss is of two types. The first absorption loss is nothing but it is called as the absorption loss is intrinsic absorption. It is called as intrinsic absorption. It is called intrinsic absorption. Intrinsic absorption is also called as the IR absorption. IR stands for infrared absorption. Also called as IR absorption, which is called infrared absorption. Second one is called as extrinsic absorption. It is called as extrinsic absorption we are having. So when you talk about the extrinsic absorption, you can find out very clearly such that it is also called as the ion absorption. It is also called as ion absorption we are having. The first one is called as intrinsic absorption, and the second one is called as extrinsic, also called as ion absorption we are having. So this is completely about the concept we have. So please see here, talking about the intrinsic absorption or extrinsic absorption we have. I can explain this thing to you clearly. So this is the fiber we are having. So देखो भैया, ये हमारा fiber है, core and claddy. refractive index of core is equal to N1, refractive index of clad is equal to N2. Okay. So, these are the glass molecules we are having, the atoms of the glass molecules, atoms of the glass molecules of the core. These are the glass molecules. These are called atoms. These are called atoms of glass glass molecules in core. Okay, glass molecules in core we are having. So, what happened is, whenever the light is passing through this atoms of the glass, they are start absorbing this light. Such absorption is called as intrinsic or IR absorption. We cannot eliminate that. We cannot eliminate it. The reason is because glass is going to be, when infrared light is passing through it, glass molecules are start absorbing some light, and because of that, whatever the input power we are giving, the output power what we obtained is very, very less. So, what the power we gave and what the power we got are not same, bhaiya. Okay, they are not same. The reason is because of these atoms are absorbing the power, the amount of power getting at the output is very, very less. So, this absorption is called as intrinsic absorption or IR absorption we have. So, next one, coming to the next one, we can tell about the extrinsic absorption. Bhaiya dekho bhaiya, extrinsic absorption, if you talk about the extrinsic absorption, it looks like this. It is called as the extrinsic absorption we are having. So, once we talk about the extrinsic absorption or ion absorption, it is due to the OH minus ions. OH minus ions. What is this OH minus ion? The source of OH minus ions is, OH minus ions is, the source of OH minus ions is, OH minus ions is water. So, when you are mixing a water, you are definitely going to be having that water is mixed, and mixing of that water will definitely have trapped some of the OH minus ions in the fiber. And then when the light is passing through that OH minus ions, they start absorbing it. Okay, and some metal impurities or metal element impurities are also present in the fiber, will start absorbing that optical signal which is passing through a fiber. Because of that, what happens is the amount of power received at the end of the fiber is very less because of this absorption. So, see here bhaiya, when I am sending an electromagnetic signal, light through it, it absorb it, the strength what we are having is becoming very, very less. The source of the OH minus ions, what the source of the OH minus ions we are having is very, very important, is water. Because of that water only it is present, and it is not possible to eliminate also, but we can decrease it. That means we can select a fiber which is having less OH ions by checking the ppm. ppm stands for the part per million. So, how many number of OH minus ions are there? So, part per million we can get. So, consider a fiber which is having less amount of the ppm, that is part per million are there. So, we can consider that fiber. Therefore, automatically what happened is the amount of loss that we are having is very, very less. Okay, this is called as absorption loss. So, this loss will comes under the category of manufacturing loss. It is comes under the category of manufacturing loss. So, it is the manufacturing loss we are having bhaiya. So, hope everybody in the class understood this. So, please copy it, Nana. If copying is completed, please drop a message so that I will tell the points as a note to you. The points as a note to you if copying is completed. Right. Please write on the first point, all of you. Write on the first point. The impurities in the fiber, the impurities in the fiber, the impurities in the fiber absorb the light. The impurities in the fiber, first point, the impurities in the fiber absorb the light, absorb the light, absorb the light and dissipated in the form of, absorb the light and dissipated in the form of heat, and dissipated in the form of heat, dissipated in the form of heat. Right. Next point, dissipated in the form of heat. Point number 2. Point number 2. Absorption loss is of two types. Absorption loss is of two types. First one is, absorption loss is of two types. First one is intrinsic absorption, intrinsic absorption or IR absorption. IR stands for infrared. IR stands for infrared. IR stands for infrared. Intrinsic absorption or infrared absorption, or infrared absorption. Right. Next one. Second one is extrinsic absorption, extrinsic absorption or ion absorption, ION. Extrinsic absorption or ion absorption, extrinsic absorption or ion absorption, or ion absorption. Okay, right. Put the heading as intrinsic absorption. Put the heading as intrinsic absorption. Intrinsic absorption. First point. This absorption is due to atoms of the glass. This absorption is due to atoms of the glass molecules, atoms of the glass molecules in the core, atoms of the glass molecules in the core is due to atoms of the glass molecules in the core absorb the infrared light, absorbs the infrared light, okay, absorbs the infrared light. Right. Next one. Next one, please put the heading as extrinsic absorption. Extrinsic absorption. Extrinsic absorption. It is due to OH minus ions. It is due to OH minus ions and metal element impurities. It is due to OH minus ions and metal element impurities that are trapped in the fiber, during manufacturing process. During the manufacturing process. Okay, right. During the manufacturing process. Next point. The source of OH minus ions. The source of OH minus ions is water. The source of OH minus ions is water. And can be measured as part per million, ppm, and can be measured as part per million ppm, part per million, can measured as ppm part per million. So I hope everybody in the class understood this one, absorption loss. Bhaiya, points also completed and also measured as ppm part per million. Okay, so I am starting the next one, that is called as your next loss is called as scattering loss. That is given as scattering loss. देखो भैया, scattering loss, name something suggesting by the name itself only, scatter. Scattered means it diffracts in all the directions. Okay, scattering in all the directions means diffraction in all the directions. I hope everybody in the class understood this. That is, diffracted in all the directions is called as scattering, which is called as scattering loss we are having. So once we talk about the scattering loss, we can tell such that it is of two types. Bhaiya, scattering loss is of two types. First one is called as your linear scattering. Dear students, please concentrate, which is called as linear scattering we are having. So देखो भैया, दूसरा वाला है ना non-linear scattering. Good, non-linear scattering. So first scattering is called as linear, second scattering is called as which one, Anna? Non-linear scattering we are having. So once we talk about the linear scattering, I will tell like this. So talking about the linear scattering thing. So linear scattering is once again of two types, which is said to be called as Rayleigh scattering. It is called as Rayleigh scattering, which is also called as Rayleigh scattering loss. It is called as Rayleigh scattering we are having. Second one is called as Mie scattering. It is Mie, M-I-E, Mie scattering, not M-Y. It is called as M-I-E bhaiya, Mie scattering we are having. So please all of you understand the concept carefully bhaiya. We see about that because of the OH minus ions, because of the glass molecules, because of the atoms, all are absorbing the energy and creating a problem for us, decreasing the signal strength. And you are expecting that your P out is always less than the P in. Okay, so then what we are trying to doing right now is we are talking about the second reason why our Pout is getting very less. If Pout is becoming less in the sense means we can tell such that your attenuation is becoming very high, because alpha is equal to P in by Pout nana. So Pout is becoming less in the sense means alpha definitely increases. So attenuation increases. First problem we are facing is decreases the bandwidth by a, decreases the bit rate by a, and also overall system performance will be very less. So we don't want our attenuation to be affecting on our optical communication system. That's why we are studying each one in detail. Now I can explain the concept of scattering loss. So देखो भैया scattering loss के लिए इधर देखो एक बार हम क्या करेंगे, डोपिंग किया. सी भैया देखिए इधर डोपिंग किया. So this is the doping. You perform the doping. See, I perform the doping. By performing the doping, what happened? Your core of pure form of glass is converted into claddie because of N1 refractive index changes to N2. But of course, N1 and N2 are approximately same bhaiya. They are very close to each other. So we understand clearly from this instance such that doping ions will be doped uniformly on both the two sides of the fiber. On both the two sides of the fiber, doping will be done uniformly throughout the length of the fiber. So when I talk about uniformly throughout the length of the fiber, doping is done, then there is no issue. But what happens about the Rayleigh scattering, I will explain. Please see here. So observe here carefully. So थोड़ा important concept question आ गया हमको. So इसी के लिए थोड़ा कंसंट्रेट करो. वेरी इजी बट थोड़ा इम्पोर्टेंट है. दैट्स इट. So Rayleigh scattering. Now once we talk about the Rayleigh scattering, we study in the classroom. It is the core via and it is the claddie. So core and claddie. So claddie is formed. Claddie is formed means doping is done. So doping is done. This is N2, this is N1, and this is N2. So whenever the doping is done, if any one of the doping impurity is deeply penetrated into the core, this is a doping impurity. What is this one? Doping impurity. So one of the doping impurity is deeply, so this is called as doping impurity bhaiya, which is called as doping impurity. So doping impurity we are having. So this is the doping impurity. So the doping impurity has deeply penetrated into the core. And when you are sending a light signal passing through this one, see, I will change the color. Okay. So I am changing the color, red color. So I think it's visible for you for the red color. Whenever I am sending the doping impurity, then what happens means suddenly this light will going to be hitting the impurity and it will scattered in all the directions. It is scattered in all the directions. The light is scattered in all the directions. So whenever the light is scattered in all the directions, two things will happen. One is whatever the light that is scattered will going to be escaped through the claddie, and it is going to be scattered, came out from the claddie bhaiya. From the core, it escapes through into the claddie. So light which goes into the claddie is not useful to us, and only some part of the light will propagate down the fiber. Only small part of light can be propagate down the fiber. May or may not propagate down the fiber. Okay, if it is propagated, we are happy that depending upon the size of the doping impurity. For example, size of the doping impurity is very high. The amount of light that passes to the other end of the fiber is not possible. But if the doping impurity is very less, then it is possible for us to have a light to pass into the other end bhaiya. So this is what said to be called as scattering. This scattering, so light is diffracted in all the directions. Some of the light is escaped through the cladding and some of the light will propagate down the fiber, and this is said to be called as the such scattering or such diffraction. What we are having is called as Rayleigh scattering. It is proposed by the name of a scientist who is called as Rayleigh. I hope you studied in signals and system about the Rayleigh energy theorem. The same Rayleigh energy theorem what have the Rayleigh scientist, and this scientist are going to be the same which proposed this concept, which is called as Rayleigh's scattering loss we are having. Okay, this is called Rayleigh scattering loss is present. So hope everybody in the class understand. For example, the doping is done perfectly by the manufacturer, then there is no impurity present in the core bhaiya. There is no impurity present in the core, then occurrence of diffraction is very, very less. And such care has to be taken by the manufacturer when he was manufacturing a fiber. It is not like that much easy that every company will going to be manufacture a fiber bhaiya. More care has to be taken for manufacturing a fiber. Okay. So next important one, that is my scattering. Please bhaiya, thoda concentrate karo. Pehla I will explain the reason, then I can explain the concept, such how it is having a scattering. देखो भैया एक बार a diagram को ध्यान से सुनो. See here, I am explained here already to you one small point, that is whenever we are talking about the fiber, the fiber is making that for having a length of a fiber other than the doping, you are also performing one operation called as rolling. And what is this called as? These are called as rollers. Okay, we have them, these are called as rollers we are having. These rollers are continuously rolling the fiber to have a length, because from a molten glass you are continuously rolling to make to get the so called length of the fiber of 10 kilometers is required. And in the process of such rolling, what happens is an external pressure will falls on the fiber. When the external pressure falls on the fiber, it is going to be changing the molecular structure of the fiber. So molecular structure of the glass will changes by the external pressure, which is formed by the rolling of long distance, because for the requirement of long distance you are rolling the fiber, and that is going to be making an effect and creates a scattering called as my scattering. I hope everybody in the class understood this. So need to explain you about the my scattering bhaiya. My scattering is obtained because of this rollings, because of the rolling of the fiber, and it is mandatory for us to roll the fiber. We cannot, without rolling the fiber, it is not possible for us to manufacture the fiber also. But while rolling the fiber, make sure such that may not be have more pressure has to pressure on the in the fiber. Okay. Now see here bhaiya, when you talk about the my scattering, so here I am explaining you about the my scattering. If you see that my scattering, this is about the my scattering. First your core is rolled. This will going to be make deformation in the structure of the molecular structure. See, the structure is changed. You observe here carefully bhaiya. The remaining structure is going to be looks like a hexagon. Wherever we have a rolling operation, your fiber has to be changed its structure. So here this is the exact structure by actually we have this hexagonal structure is present, which is the exact structure. There is no pressure on this one, but due to the pressure here what happened, the structure is changed. Now just observe it. Whenever the light is moving, see clearly bhaiya, when the light will come and strike here, what happens, deformation in the molecular structure of the glass will make this light to diffract in all the directions like this, which is as shown in the figure, which will diffract in all the directions is called as my scattering we are having. Such scattering is called as my scattering we have. So this is the concept of linear scattering. So when you see about the linear scattering, it is the second one which is called as my scattering we have. Next one, after that we can have a non-linear scattering. So bhaiya dekho, non-linear scattering is of two types once again. So I will just explain you about the non-linear scattering also. So clearly listen, very simple to understand here. One is called as SRS. SRS stands for the stimulated. It is called as stimulated Raman scattering. So stimulated, it is called as Raman scattering we are having. So stimulated Raman scattering is present. And the second one is called as SBS. SBS is called as stimulated. It is called as stimulated beryllium. Okay, beryllium scattering. Stimulated beryllium scattering we are having. So it is the name of the scientist one name of scientist is Raman, another name of the scientist is beryllium. So, stimulated beryllium scattering is this one. So, SBS is called stimulated, SBS is stimulated beryllium scattering, SRS is stimulated Raman scattering we are having. So, what exactly here happens is, I will just explain to you. Please understand. First of all, I am explaining the SRS, it will point in the notes clearly. So, whenever we are going to be talking about the SRS, stimulated Raman scattering, when the light is passing through the optical fiber cable, the glass atoms of glass molecules absorb that light energy and get excited with that energy and move random fluctuations like stimulated and move random fluctuations like this, which is affecting on the transmission of your signal through pass into the fiber. Because of this random fluctuation, what happened means it will affecting the signal to have a loss in the transmission of the signal, which is called stimulated Raman scattering we are having. Because of that electrons are going to be stimulated, we get a scattering there. And the next important one is, see, observe here, SBS, stimulated beryllium scattering. If you observe here clearly, you understand here, from this part you get it clearly. Once we are talking about this scattering is there, some of the light is going to be moving in the backward direction. See, light is moving in the backward direction. This backward light is going to be making an opposition to the forward, and some of the energy of your backward will going to be added to the forward light, and therefore it is going to be upsetting it. Because of this the electrons are get stimulated there itself, and it is creating some scattering, which is creating a power depletion. A power depletion is formed by using SBS. I will explain once again, please, no confusion, get a clarity in a single line I can tell to you. Because of absorbing the energy, light energy or light power by the glass molecules get stimulated and creating an obstruction for the light to pass into a fiber. Whenever we are having the diffraction, when the diffraction occurs, the forward path is obstructed by the your backward path. In this process, power depletion occurs. This is completely what we call it as our scattering. One is called linear scattering, other one is called as nonlinear scattering we are having. So, 4 scatterings bhaiya. So, please see here, one is because of doping impurity, light will diffracted in all the directions, called Rayleigh scattering. Second one is because of rolling, some deformation in the structure of the glass and makes the scattering is called as Mie scattering. Because of absorbing the energy, glass molecules will get excited and stimulating and get moving like this stimulation will create a problem called as SBS. And because of the backward path is going to be objecting the forward path, a power depletion is formed, and because of that reason we call it as SBS, stimulated beryllium scattering. I hope everybody in the class understood this. So, these 4 points are very, very important. You please copy this. Once copying is completed, put a message so that I can start explaining you the notes for this one. Yeah, Sagar, my scattering is getting due to the rolling only. Because of rolling, deformation in the structure of the glass will have that problem. Yeah, copying is completed. Can tell the first point as a note. Write on the first point. Write on the first point. Scattering loss, first point. When the light propagating through a fiber, when the light propagating through a fiber hit the impurities, when light propagating through the fiber hit the impurities and diffracted the light in all directions, right. Second point, diffracted the light in all directions. Second point, point number 2, this diffracted light, can escape through the cladding, and small portion of light may or may not propagate down the fiber, and a small portion of light may or may not propagate down the fiber, may or may not propagate down the fiber, may or may not propagate down the fiber, may or may not propagate down the fiber. Okay, right. Next one. May or may not propagate down the fiber. Next one. This loss due to the diffraction, this loss due to the diffraction is said to be Rayleigh scattering loss, is said to be Rayleigh scattering loss, said to be Rayleigh scattering loss. Okay, right. Next one. Next one. Please put the heading as my scattering. My scattering. My scattering. Okay. My scattering. First point. My scattering is due to molecular deformation in the structure of the glass. My scattering is due to molecular deformation in the structure of the glass. When light is in the structure of the glass, when light is due to molecular deformation in the structure of the glass, when light is diffracted, okay, right. Please put the heading as SBS, SRS, first stimulated Raman scattering. Right. When the glass molecules absorb the light energy, and excited, yeah, please put the heading as SBS, stimulated beryllium scattering. SBS. Yeah, write down. The diffracted light, SBS, first point, the diffracted light opposes the momentum of the forward light, which creates power depletion. Okay. So these things are the points as a points note. Okay. SRS and SBS. So next one, I hope copying is completed. Next one, is called as waveguide bend losses. Your waveguide bend losses are also called as radiative losses. are also called as radiative losses. So, waveguide bend losses are also called as radiative losses. So, before going to explaining you this one, I will tell like this. So, these losses are occurring due to installation, Second one is or handling the fibers. During handling the fibers, we have some tension when handling the fibers. Because of that tension, we are having the problem called as your waveguides, creating a loss called as waveguide bend loss is present. So, waveguide bend losses is of two types. First one is said to be called as the macro bend loss. Second one is called as micro bend loss. Okay. So, having the micro bend loss is present. So, first one is called as your macro bend, second one is called as micro bend loss. Okay. So, the two types of bend losses we are having. So, please here concentrate Bhaiya for 2 minutes of time. Whenever you are going to be having a fiber is bended as shown in the figure like this. This is clady Bhaiya bend ho gaya. I hope everybody in the class understood this. This is core of the fiber. So, fiber is bended as shown in the figure like this. Strictly speaking, you are going to be having an axis looks like this. This is the fiber. Because of bending, what happened is, because of the bending, it is changing from its original shape, bend like this. I hope everybody in the class understood this. Please listen. Later on we can write it, no problem, I give time. Just try to understand. Okay, just see here. So, macro bend loss we are having, talking about the macro bend loss. So, we can tell about that our light signal is passing through it. Bhaiya concentrate करो. इधर से start हो गया here and when it want to hit here, just see the difference here Bhaiya. I hope everybody will observe here clearly at this point. At this point actually because of the bending, it is not going to be hitting the border, the boundary between the core and clady, Then the angle of incidence was changing comparing with the critical angle. Yes or no? If it is greater than the critical angle, then there is no problem. The light will get reflected, takes TIR. But if that light, incident light, see this light which is incidenting is less than the theta c, what happens is this light ray will pass into the clady and lost it. So, because of the bending, what happening is two things. The light may take TIR, total internal reflection. Because of the total internal reflection, it may hit multiple times and once again loses the signal strength. Or second important thing what happens is very clearly that is nothing but n, we can tell like this, the second important point is the light ray may get lost in the clady. So, this is the one beautiful thing that you need to understand while handling or while installing You cannot make your fiber to bend as your choice. Why? Because of that bending, the light rays may get multiple reflections, more TIRs, then also some loss, and or the light ray may escape through the claddie, completely the light ray may also be lost it. This is the problem that we are facing with bending. Now, I can tell like this. So, try to concentrate Bhaiya. For example, if I am bending the fiber with very large radius, this is called as radius of curvature. Students follow Nana. It is a radius of curvature. So, I am bending the fiber with a large radius, core radius, this is called as curvature. So, radius of curvature with a large radius I am making a bend, then amount of loss that offers is very less. So, whatever the loss we are having, that loss is very less. Why? Because means it is very clear such that fiber is bending with a large radius, the impact of changing of the incidence angle cannot be done that much, cannot be affect much on the your fiber. Okay. So, that is a bending with large radius, your attenuation will be less, your loss will be less. For example, if you bend the fiber with very small radius, see small radius of curvature, this is the bending with small radius of curvature, your RC is very small, definitely your attenuation is very high, such that we cannot receive the output power also. In the final year of BTech, in our project in laboratory, we done this experiment, optical lab. In that, you can make your fiber to bend with large radius. When you bend the fiber with large radius, okay, then the amount of loss offered is very less. But when you bend the fiber with very small radius, we may not receive the power at the output side also. Entire power is lost because the mode is lost. The light what you are sending is lost to the claddie. So, whatever the power getting at the other end, no power is received. So, this phenomena is called as bending, is called as which bending? Macro bend loss we are having. Then we can have some formulas that what is the radius of this curvature formula I am having, I can explain to you. So, please concentrate Bhaiya. When we talk about the single mode fibers, writing the single mode fibers. So, in single mode fibers I am writing the bend radius. So, discussing about the single mode fibers. So, single mode fibers, your bend radius is given as RC. RC is called as the radius of the curvature. RC stands for radius of curvature. So, curvature is equal to given as 3n1 square into lambda divided by 4 pi into n1 square minus n2 square whole to the power of 3 by 2. Observe carefully, the radius of the curvature or the bend, how much amount of bend the fiber has to be present in single mode fiber is depends upon the refractive index of core and claddie, and also depends upon the wavelength lambda. Okay, wavelength lambda. Now, observe carefully guys, if lambda is operating wavelength is going to be high, then the radius of curvature is also increases. Obviously, it is going to be having the high amount of radius of curvature has to be required. So, that depends upon the two important parameters, one is on the wavelength and another one is on the N1 and N2. I hope everybody in the class understood this. So, this formula is very much important Bhaiya. That's just understand that radius of curvature is depending upon the two important things. One is refractive index of core and claddie, another one is wavelength. Sahi hai. Now, I will tell about the same explanation. So, I can write here Bhaiya, I can write here. So, thoda space problem aa gaya. I want to fit it in this screen only. So, I am trying my level best to fit in the screen for multi-mode fibers. For multi-mode fibers. So, we are discussing about the multi-mode fibers. If you talk about the multi-mode fibers, you can tell very clearly your RC value, so radius of curvature is equal to, so value is given as 20 lambda divided by n1 minus n2 whole to the power of 3 by 2 into 2 point value is equal to 748 minus 0.996 lambda divided by lambda c whole to the power of minus 3 we are having, whole to the power of minus 3. So, I hope everybody in the class understood this. So, Bhaiya, dekho Bhaiya. So, this is the formula we are having. So, it is the formula we have for the single mode operation. and this is the remaining formula we are having for your multi-mode operation. That is, for your multi-mode operation we can take this value, that is equal to minus 3 we are having. So hope everybody in the class will understand this formula. So here also, what is lambda? Lambda is the operating wavelength. What is lambda c? Lambda c is the cutoff wavelength. We studied in yesterday's class, na, lambda c cutoff wavelength is given as 2 pi a into numerical aperture whole divided by 2.405. So lambda greater than lambda c, single mode fibers, lambda is less than lambda c, it is multi-mode fibers. We studied in yesterday's topic, and that is what we are seeing here, which is called as your RC, radius of curvature. So this much amount of radius of curvature I can maintain by using that formula. So right now I have a fiber, it is the fiber. The fiber refractive index N1 N2 knows to us, and also we know about the next one, that is said to be called as the operating wavelength. How much amount of light with which wavelength we are sending into a fiber also knows to us. Then what we can do, we can going to be calculate the RC, you get some amount of RC value. With that RC you can maintain a bend, greater than that also you can maintain the bend, no problem bhaiya. Then we can transmit the signal effectively. But this loss is completely man-made loss. Make sure such that whenever we are using your fiber, so make sure such that it has to be always have the bend with equal to RC or greater than RC. Clear na? Greater than RC also no problem. But less than that, what happens bhaiya? Loss is very, very high. So these losses comes under the category of man-made losses. Of course, I can add that also. Now coming to the micro bend, Nana. Coming to the micro bend. Dear students, please see here. Micro bend. So when you talk about a micro bend, this is your optical fiber with the core and claddie as shown in the figure. So it is optical fiber with core and claddie as shown in the figure like this. So this part was given like this, clamped bhaiya. So you are going to be clamping the fiber. See, we are clamped to the wall. Sometimes you can see also some of the wires are going to be clamped. For copper wires you clamped, no issues, but fiber optical cables we clamped, it creates a big problem. See, because of this clamping, your fiber is clamping, see, clamped to the wall. So fiber is clamped to the wall like this. So whenever we clamped here by putting a nail, clamped here, external pressure will falls on the fiber. Because of that external pressure, what happened is you are getting a geometric imperfection. It's a geometric imperfection. So we can find the geometric imperfection as shown in the figure. So bhaiya, it is called as geometric imperfection we are having. So as shown in the figure like this. So here also you are going to be having the geometric imperfection because of that excess pressure we are having on your fiber and core, and this will going to be affecting mostly. So as shown in the figure like this. So it is called as the pressure that offered by the clamp will making you the geometric imperfections or miniature changes in your core, which is very small changes in the core will present like this. So whenever the light, see red color I am doing, whenever the light will come and pass, so when the light is come and hit this structure, because of imperfection, it will takes place scattering in all the directions, it will takes place Rayleigh scattering because of that geometric imperfection present in the fiber due to external pressure you are putting on your fiber is called as very small miniature imperfection we are having. Because of that miniature imperfection we are having the loss and scattering, Rayleigh scattering occurs. This is called as micro bend. That's why whenever we see the installation of fibers, they don't use the clamps, all those things for your optical cable, where for internet when you connecting a Wi-Fi. You know about that, some plastic threads are there, you put it and lock it like this. So they will put those threads and lock the cable. Thus the cable is hanging. So the cable is not clamped and they are not going to be putting any pressure on that to avoid the micro bending. A good technician can always make sure such that fiber has to be made with bit round, with more radius, it has to make a curvature, first thing. And second important thing you can find out is a good technician can never be clamp your optical fiber cable bhaiya. So these losses are completely we are having, which are said to be called as the man-made losses. So these are called as man-made loss we have. So I hope everybody in the class understood this topic. It is called as man-made loss. Please copy it, Nana. Complete na copying? Yes. Copy. Write down the points as a note. First point, radiative losses. Radiative losses are due to small bends, are due to small bends, due to small bends in the fiber, due to small bends in the fiber, due to small bends in fiber, right, due to small bends in fiber. Next point, radiative losses are of two types. Radiative losses are of two types. Radiative losses are of two types. First one is macro bend. First one is macro bend and second one is micro bend. First one is macro bend, second one is micro bend. Yeah, put the heading as macro bend, macro bend, these losses occurs, macro bend, these losses occurs, these losses occurs when fiber is handling and installing, when fiber is handling and installing handling and installing, right. Next point, handling and installing. Next point, macro bend loss depends on the macro bend loss, macro bend loss depends on the macro bend loss depends on the radius of the curvature, depends on the radius of the curvature of the fiber. Radius of curvature of the fiber, radius of curvature of the fiber. Next point, point number 3. When the fiber is bent, with large radius, when fiber is bent with large radius, then fiber is bent with large radius, then radiative loss is less, then radiative loss is less, then radiative loss is less, radiative loss is less, full stop. If fiber is bent with small radius, if fiber is bent with small radius, is bent with small radius, then loss is very high, then loss is very high, then loss is very high. Okay, right. Next one. Please put the heading as micro bend loss. Put the heading as micro bend loss. Micro bend loss. Right. First point. It is due to miniature. It is due to miniature and geometric imperfection. Geometric imperfection. GEOMETRIC. Geometric imperfection. Geometric imperfection across the axis of the core. Geometric imperfection across the axis of the core. Miniature and geometric imperfection across the axis of the core. Across the axis of the core. Axis of the core provides Rayleigh scattering. Across the axis of the core provides the Rayleigh scattering. Provides the Rayleigh scattering. Provides the Rayleigh scattering. Provides the Rayleigh scattering. Full stop. Due to this scattering, loss occurs from the external pressure. Due to this diffraction, loss occurs from the external pressure. From the external pressure. From the external pressure. External pressure. Okay, bhaiya. Last point. Radiative losses are man-made losses. Please underline man-made losses, Nana. Radiative losses, भैया underline man-made losses. Radiative losses are man-made losses. Are man-made losses. Yeah, please underline that. Please underline that. I will explain the next concept. I hope you copied everything, right, bhaiya? So I got a message from few students. From Radhika, from A.R. Singh, Radhika Devi and A.R. Singh, I got a message. So I can explain you the next concept. Okay. So that is called as core and clady loss. It's called as core and clady loss. Please listen this concept. I give time for you to copy, don't worry. Please listen this concept, Nana. Important concept. थोड़ा concentrate करो. Easy, बहुत easy है. Core and clady loss. Core and clady loss. Don't worry, I will make it very easy, भैया. भैया, just understand the concept, भैया. So ये हमारा फाइबर है, कोर और क्लैडी. कोर का रिफ्रैक्टिव इंडेक्स N1 है, क्लैडी का रिफ्रैक्टिव इंडेक्स N2 है. इधर लाइट सोर्स से हम लाइट कपल करने के लिए, फाइबर के अंदर सेंड करने के लिए, लाइट सोर्स से लाइट कपल करने चाहिए. So red color indicates the light भैया. So light couples अंदर चले गया. देखो इधर थोड़ा पार्ट क्लैडी में है, इधर ही थोड़ा पार्ट क्लैडी में है और ज्यादा पार्ट कोर में है. ये पावर कोर में है, ये पावर क्लैडी में है. सो इतना पावर कोर में है वो पी कोर है. हम पी कोर पूछेंगे. इतना पावर क्लैडी में है ये पी क्लैडी है, पी क्लैडी पूछेंगे. ठीक है ना. हम देखो भैया कोर का रिफ्रैक्टिव इंडेक्स n1 है. n1 विल हैव द एटेन्यूएशन कोएफिशिएंट. कंपोजिशन अलग अलग रहेंगे. क्लैड के लिए अलग है, कोर के लिए अलग है. कंपोजिशन डिफरेंस हो गया. इसी कंपोजिशन डिफरेंस में क्या करेंगे, हमको n1 के लिए अल्फा 1 बोलेंगे. सो बिकॉज ऑफ द चेंज इन द कंपोजिशन वी आर हैविंग रिफ्रैक्टिव इंडेक्स ऑफ n1. सच n1 रिफ्रैक्टिव इंडेक्स provides an attenuation of alpha 1 and such alpha 1 attenuation is presented given by the core. Similarly भैया alpha 2 composition of clady. So clady का composition अलग अलग है, इसी के लिए उसका attenuation constant के लिए alpha 2 बोलेंगे. So alpha 1 एटेन्यूएशन ऑफ क्लैड है, सॉरी कोर है. अल्फा 2 एटेन्यूएशन ऑफ क्लैड है. ठीक है भैया. सो समझ हो गया. सो अभी तो क्या करेंगे, सो लाइट सोर्स से पावर आ गया, ए पावर का पी बोलेंगे, ये पी है. सो लाइट सोर्स को कितना पावर फाइबर के पास करने को और फाइबर को कपुल करने को वो पावर पे पी पूछेंगे. सो इसी के पी पावर, इसमें पी पावर में थोड़ा पावर क्लैड में है, ज्यादा पावर कोर में चलेंगे. बट थोड़ा पावर क्लैड में कपल हो गया, ये हमारा वेस्ट के लिए. वेस्ट में क्या होंगे, लॉस का बोलेंगे. सो वी आर लॉसिंग दैट पावर. सो इसी का प्रॉब्लम को हमको एड्रेस करने के लिए कितना पावर क्लैड में लॉस हो गया वो क्लैड लॉस है, इतना पावर कोर में भी लॉस हो गया वो कोर लॉस है. सो थोड़ा पावर क्लैडी में चलेंगे, इसी पावर कोर में चाहिए हमको, वो लॉस को पूछेंगे. ठीक है भैया. आई ट्राई टू टेल इन हिंदी. आई थिंक आई मे नॉट बी दैट मच सक्सीड. आई विल एक्सप्लेन दिस पॉइंट वंस अगेन. सी हियर, एक्चुअली टोटल पावर इज P, total power is P, and that power, total power P what you are getting is has to be go into the core, but due to bad coupling or due to some reasons some power is going into the clady is lost it. So actually power has to go into the core, due to power goes into clad, it is wasted or it is created as a loss. Therefore what we are doing is, see bhaiya, power P, understand the concept, power P total power generated by the light source है. Power P is equal to power present in the core plus power present in the clad. So समझ गया. So core से थोड़ा पावर है, clad का पावर है, दोनों को ऐड करने के लिए पावर P आ गया. वो पावर क्या है, लाइट सोर्स का पावर है. सो लाइट सोर्स का पावर P है, पावर P इज इक्वल टू P कोर प्लस P क्लैड है. सो P कोर प्लस P क्लैड आ गया भैया हमको. सो अभी तो क्या करेंगे हम, राइट. सो डिवाइडेड बाई P करेंगे बोथ द साइड्स. सो बोथ द साइड्स P से डिवाइड करो भैया. सो P कोर बाई P है प्लस P क्लैड बाई P है प्लस P क्लैड बाई P है. सो P बाई P कैंसिल आउट, ये दोनों कैंसिल आउट हो जाएंगे. देन वी गॉट द वैल्यू ऑफ P क्लैड. देखो भैया P क्लैड बाई P इज इक्वल टू P बाई P इज इक्वल टू 1 भैया, 1 माइनस ये अदर साइड चल गया, इज इक्वल टू P कोर बाई P आ गया. दैट्स इक्वल टू P क्लैड बाई P इज इक्वल टू 1 माइनस P कोर बाई P आ गया. ओके देखो भैया. सो इफ यू टॉक अबाउट दिस वन, दैट इज पी क्लैड बाई पी इज इक्वल टू 1 माइनस पी कोर बाई पी, हमको फॉर्मूला आ गया. सो इधर एक बार पूछेंगे पी क्लैड बाई पी भैया, पी क्लैड बाई पी कामा पी कोर बाई पी कोर बाई पी. व्हाट्स द मीनिंग ऑफ दिस वन इज, हमको टोटल पावर पी है, इसमें थोड़ा पावर क्लैड में है, टोटल पावर पी है, इतने ज्यादा पावर कोर में है. ओके कोर में है. ये का नाम क्या है, ये फ्रैक्शनल पावर्स बोलेंगे. वाई इट इज कॉल्ड फ्रैक्शनल पावर, टोटल पावर पी में थोड़ा पावर क्लैड में है, टोटल पावर पी में ज्यादा पावर कोर में है. सो आउट ऑफ दिस इट इज कॉल्ड फ्रैक्शनल पावर वी आर हैविंग. So it is called fractional powers we are having. So I hope everybody in the class understood this. So I will tell in English. Okay, I try to tell in Hindi. I don't know how much you understood, but I tried it just. So see here, all of you please understand this part. I'll explain in a very few points. Just in 3 steps I will explain. So whenever we are coupling a light from light source into a fiber, okay, some part of the power goes into claddie because of the bad coupling, okay, because of the bad coupling, and that power which goes into the claddie is considered to be as a loss, okay, because the total power produced by the light source is P. Actually you want to send this entire power P into the core only, but it is not possible. Some power is going into claddie. That is the reason the power present in the core is not the total power P, that is P core. Similarly, the power that is present in the claddie is not the power P, that is a part of the power P. It's clear, Nana? So the first step. Second step is, what is the power P that you are sending is moves into core and claddie, thus a combination of those two. So total power P is the power present in the core and the power present in the clad. Clear, Nana? Second point. Now in that point I am writing P core by P, P clad by P. The second point only, P core by P, P clad by P is called as fractional power. So how we write a fraction? See how we write a fraction? 1 by 4. What's the meaning of this one? Total parts are 4. Out of that 1 by 4 we are having. See, total power is P. Out of that, power in the clad is P clad by P. Power in the core is P core by P. That's why it's called fractional powers, Nana. It's called as a fractional powers. Clear, na? That's the second point. But coming to the third point, that's a little bit important point. Actually, I explained to you. N1 refractive index of core, N2 refractive index of claddie. You knows that N1 and N2 differ in their composition. When they differ in their composition, their refractive indices will be different. When the refractive indices will be different, the attenuation offered by the two different elements or two different materials is also different. Clear, na? Point number 3, Nana. Point number 3 already explained that in Hindi, but I am explaining once again in English. Now see here, whenever we talk about the point, point number 3, so the material composition of core and the material composition of clad are different. Then automatically the attenuation offered by the core and the attenuation offered by the claddie are different. That's the point number 3. Then we denoted attenuation of core as N1, attenuation of claddie as N2. Sorry, alpha 1 and alpha 2. Okay, so bhaiya, please see here. I am explaining you about a small calculation to you. Please see here. The attenuation offered, by a single mode operation is alpha is equal to, see attenuation offered. Bhaiya dekho bhaiya, how much attenuation we are getting right now? The attenuation that we are getting is, see here carefully, alpha 1. This is the attenuation offered by the core. For example, total power P goes into the core only. then attenuation alpha is equal to alpha 1 only, because entire power is going in the core itself only. Am I clear? Okay, but right now entire power is not, P is not going into the core. How much power is going into the core? That is P core by P. इतना fractional power चलेंगे core में. So that is alpha 1 into the value is equal to P core by P ना plus, देखो भैया alpha 2. Alpha 2 is nothing but and it is equal to P clad by P. So this is completely what we are having is called as your alpha attenuation. I want to give you a simple explanation here for this attenuation. So why I wrote this formula I can explain to you. You can going to be understand very easily once I explain that part to you. भैया देखो भैया देखो. For example, if you make coupling very effectively, entire power goes into the core only. Clear na? Entire power goes into the core only. If entire power is going into the core, see, observe it, entire power going into the core, P core and P are same. Am I clear? Then what is P clad? P clad is 0. I will write that, then you understand very easily, Nana. See, whatever the power I am sending, entire power goes into which one, Nana? Power goes into the core only. Whatever the power I am sending, entire power goes into the core only. Then obviously what happened? Your P clad is equal to 0, because there is no power in the clad. Bhaiya, observe this part. If P clad is 0, then your power P is equal to which value? P core. See in this equation, if I can put my P clad is 0, this term becomes 0, and P is equal to P core and P are same, cancelled out bhaiya. This term is 0, these two are get cancelled out to each other, then left over is alpha 1. That means whenever you are going to be putting this condition, entire power that generated by the light source or emitted by the light source is passed into the core, then obviously what happens is, similarly power in the claddie becomes 0, then attenuation, total attenuation you wrote here, see the attenuation offered by a single mode operation you wrote here is attenuation due to the core only. ठीक है भैया? If you understand this point means, then you understand very easily why I wrote this equation, how I wrote this equation, because attenuation offered is alpha 1, but amount of power going into the core is fractional power only, P core by P, and because of the P core by P fractional power, other attenuation is offered by the claddie also considered, that is called as plus alpha 2 into P clad by P. I hope everybody in this class understood this. If you, this is a very important point, Nana. Even I tell the same point in the offline class also, I stress this point. The reason is, you have to know to by heart anything. Here this is fully, completely conceptual, nothing to by heart anything by here. Some completely conceptual. It's not a fact also, it's a process. It's a process of taking. Okay, so process of taking the attenuation. So total attenuation considered here is attenuation of core and attenuation of claddie. ओके ना नाउ सी हियर, देखो भैया हमको अभी तो कोर लॉस और क्लैडी लॉस का बोलेंगे. देखो भैया, ऑल ऑफ यू सी हियर, आई एम एक्सप्लेनिंग अबाउट द कोर लॉस. यू नीड टू कॉन्संट्रेट फॉर 2 minutes. आई वेरी सिंपल इट इज, आई मेक इट वेरी सिंपल फॉर यू, डोंट वरी मच अबाउट दैट. अल्फा भैया, अल्फा इज इक्वल टू अल्फा 1 इंटू पी कोर बाई पी, एम ए क्लियर ना, प्लस अल्फा 2 इंटू पी क्लैड बाई पी. What is the value of P clad by P? See this formula. देखो इधर देखो. Okay, I already wrote it. P clad by P is equal to कितना है? Very good. 1 minus P core by P. Very good, Nana. Very good. All of you are thinking about P clad is equal to 1 minus P core by P. Good for reciting. Now see here. भैया P core by P common करो. Right? Common करो. या common करेंगे भैया. Alpha 1 minus alpha 2. Like this we will get. Okay, so alpha 1 minus alpha 2, देखो भैया alpha 1 plus alpha 2 minus alpha 2 into P core by P. So हम P core by P को कॉमन किया, मालूम हो गया ना. Okay, can tell the value Nana? Plus alpha 2, and this is called as alpha, which is called core loss. This loss is called as core loss. Now we are calculating the effect. See, if only power goes into the core. Observe carefully. Only power goes into the core. Into the core in the sense means definitely P core and P both become same. Am I clear na? Only power goes into the core bhaiya. Entire power. See, entire power from the light source goes into the core. It goes into the core bhaiya. Entire goes into the core. Then what happened is P core is equal to P bhaiya. See, these two cancelled out na? See, these two cancelled out. P core by P cancelled out. Cancel. Then what happened? Alpha 2 cancel. Left over is alpha 1. Attenuation offered by the core only. How you knows that? Obviously you given na. See, of the core attenuation is alpha 1 na. You told na, alpha 1 is nothing but it is called as attenuation offered by the core na. It's core. That's why we are having like this. It's called P core by P plus alpha 2. So can you write the clad loss also? Right? I think space is sufficient. भैया कॉपी करो भैया, जल्दी कॉपी करो. डियर स्टूडेंट्स, थोड़ा जल्दी कॉपी करो. If you complete copying, just put a message so that I can explain you the clad loss. Okay, bhaiya? I will explain you the clad loss. I just try to tell the concept in Hindi. I don't know how much I succeed. You need to tell that to me. Understood na? Not important bhaiya. Hindi or English, this is not the thing. You need to understand the concept at last. Finally, that is most important. I am deliver the concept, but you must understand each and everything very neatly, and it must be remembered for your lifetime. That's the main thing. That's very important actually. Okay, I am here to make this subject very easier for you. That's it. Not no other things. So even I will try to speak in Hindi also, but I may not get the good flow. I can't maintain the flow actually. Okay, thoda आ गया, थोड़ा चल गया, जाता आता होता, like that I will have. Because the mother tongue, guys. You are very much lucky that you are having belong to the Hindi region, but you want the zooming of this one? You are saying you want zoom or you want to decrease the size? Expansion or compression? Right. So complete copying. भैया देखो भैया. And now I am going to be writing the loss called as clad loss. Okay, so written the clad loss. So here I can make a clad loss. Bhaiya, this size is also visible to you clearly? Visible? Okay. So I am writing here the loss that is called as clad loss. Okay. So writing here bhaiya, it is called as clad loss. See this formula, it's very simple. Already studied that alpha is equal to alpha 1 into value is equal to P core by P plus alpha 2 into P clad by P is the value we are having. So P core by P and P clad by P. So bhaiya, it's clad loss, alpha is equal to alpha 1 into P core by P. I can replace P core by P. See this formula, I can write P core by P. See, P core by P can also written as 1 minus P clad by P. See, P core by P is 1 minus P clad by P. हो गया भैया, मालूम हो गया ना? Right. देखो भैया, that is equal to that of alpha 1. Alpha 1 is called as 1 minus it is equal to P clad by P. So plus alpha 2 into value is equal to P clad by P is present. देखो भैया, P clad by P. Now after writing this, what we are trying to doing is, your alpha is equal to alpha 1, that is the value, plus alpha 2 minus alpha 1 into P clad by P we are having. So this is called as core and clad loss. What the formula we are having is called as the core and clad loss is present. Okay. Once if you complete copying, please drop a message so that I can start the next concept. Note. Please tell me if it is copying is completed, please inform to me to the chat box. Write down the note, all of you. Note, first point, the core and claddy, differ in the composition or differ in the composition so the refractive index is N1 and N2 respectively. So the refractive index is N1 and N2 respectively. Refractive index of N1 and N2 respectively. N1 and N2 respectively. Full stop. Next point. Point number 2. Point number 2. Point number 2. The attenuation offered by the core and clady, the attenuation offered by the core and clady is alpha 1 and alpha 2, alpha 1 and alpha 2. The attenuation offered by the core and clady is alpha 1 and alpha 2 respectively, is alpha 1 and alpha 2 respectively, alpha 1 and alpha 2 respectively. Yeah, Vishwa, what you said is correct. Actually, we don't want to talk much about the core, because not a core loss. Our concentration is about the clad loss, because some power is passed into the clad, and because of that we are having some loss, and that loss you need to consider it. That is called as your clad loss is more important for us. So next topic I need to explain. So note is completed. I need to explain the next part. The next part is nothing but an dispersion. If you see the reasons, you understand clearly, bhaiya. We are studying each and every topic and we can talk about the next one. It is called as dispersion. Dispersion. Okay. So talking about the dispersion, the first point I want to tell to you here regarding the dispersion is, okay, dispersion is called as pulse spreading. Is called as pulse spreading. Your pulse spreading is said to be called as dispersion. First point. Second point, due to the pulse spreading, what happens is we are going to be having ISI. ISI stands for inter-symbol interference. It is ISI. Third one is, we can tell very clearly such that after this pulse spreading, it is called as ISI. Because of ISI we are having the errors. So this is what the major problem with the dispersion. So dispersion is called as pulse spreading. So pulse spread होने के लिए दूसरा सिंबल का इंटरफेयर हो जाएंगे. इंटरफेयर हो जाने के लिए रिसीवर का साइड में एरर्स आ गया. इसी के लिए थोड़ा एक्सप्लेन करेंगे हाउ एरर्स हमको आ गया. भैया ये हमारा सिग्नल है शोन इन द फिगर लाइक दिस. ए 101 मालूम हो गया. ए बिट 1 pulse of bit 1 we are transmitting. It is bit 0. We have, and this is called as bit 1. That is 101 bit you are sending. So if you take about the 101 bit you are sending, then you can find out like this. For some distance it is travels, it is spreading. First reason is this pulse spreading due to dispersion or due to more number of modes. Light travels with different modes. When light travels with different modes, what happen means they arrive at different times. Arriving at different times, what happen means the pulse is spreading. The pulse will spread like this. So if you are going to be increase the distance, length of the fiber is very high, then the dispersion was obtained like this, which is shown in the figure in this way. See, this is one symbol. Actually symbol in the sense means we are writing it as a group of bit is said to be called as a symbol, combination of that. For example, we are like this, your TS is equal to 2TB we are having. What's the meaning of this one? The duration of the timing of a symbol is equal to 2 times the bit, because 2 bits are going to be carried by a one symbol, which is called as, in communication we studied, like in our BPSK, in our ASK, in our FSK, we are focusing only on the 1 bit only. Your TS and TB both are same. But in your QPSK, you are having your TS is equal to 2 times of the TB. 2 times of the TB we are having. General formula is like this, Nana. TS is equal to N into TB by N into TB is the general formula we are having. So after writing this part, you understand very clearly such that this is the 101 bit we are having. So bit is spreaded. So we are using the decision device. So decision device means a device which is going to be works with the help of a threshold and take a decision in favor of your incoming bit it is present. For example, if your incoming bit Z is greater than VTH, decision is taken in favor of 1. Z is less than VTH, decision is taken in favor of 0. Z is greater than equal to VTH is 1, Z is less than VTH is equal to 0. This is a decision device. Dekho bhaiya, after writing this decision device, the most important thing that we can see in here is, we are talking about the threshold value. So this is the threshold value we are having. Dekho, threshold value. This is the threshold value. Now it is VTH. And this signal what you are having is called as Z. That is called as Z. See the concept here. Decision device. DD stands for decision device. ये हमारा decision device है. It will take a decision है in favor of 1 or in favor of 0, which is called as decision device we are having. So once we talk about this, it is called VTH. VTH is called as the threshold voltage. We are having threshold voltage. So Z is greater. Observe carefully. I am drawing the shaded lines. Bhaiya. So observe carefully. 1 bit duration. This bit duration is called as TB. Now within the bit duration, your Z is greater than the threshold. Decision is taken in favor of 1. See, Z is greater than or equal to VTH, decision in favor of 1. Decision is taken in favor of 1. Okay. So next one is, we are talking about the 0 bit here. See, Z is greater than VTH. Then obviously it also taken in favor of 1. So next one is, we are talking about this value called as 1. Bit 1 is present here. See, decision here also Z is greater than VTH, taken in favor of 1. This is the major problem, bhaiya. You transmitted 101 because of pulse spreading. See, this pulse is spreading. Symbols are interfere, which is called ISI, inter-symbol interference. Symbols are interfere to each other. इस interference के लिए हमको क्या आ गया? Error आ गया. 0 के लिए 1 आ गया. 0 transmitting, receiving 1. Error है. इसका probability of error बोलेंगे. Okay. So this is what said to be called as error. Error occurs. This is the main problem with dispersion bhaiya, which is called as error occurs. So error is occurring. This is the concept, because some of the students told to me such that, sir, communication is not completed. So how you knows about the ISI and all those things? Don't worry bhaiya. This is the concept of ISI. By sending a pulse called as Nyquist pulse, observe carefully, sending a Nyquist pulse, which is called as raised cosine pulse, also called as sync pulse in a simple language to understand clearly for everyone. It's a sync pulse. You can perform in the Nyquist shaping. You can avoid the so-called the error. Okay, we can avoid the error. But remember carefully one more thing, such that whenever we are going to be avoiding that error, that means the ISI can be avoided by using Nyquist shaping. When the ISI is avoided, then occurrence of error is also very less bhaiya. That's why when you are doing a bandwidth calculation, we have a bandwidth calculation for sync pulse and bandwidth calculation for your rectangle pulse also. Okay. So this is the concept. That's what we are studying in communication system. So one problem is, because of ISI we have errors. Yesterday's class also I can told many number of times about the ISI when discussing about the your SMSA fibers, MMSA fibers and MMGI fibers. Okay, in the yesterday's class. Now we need to talk about the today's session. In the today's session also we came across the dispersion, pulse spreading, ISI and errors. Yesterday's class I promised such that I can explain today's class, and the day has arrived. So this is the explanation. I hope everybody in the class understood this. So once you listen the communication means no need to stress much on that. If it communication is not completed, we have to concentrate on this part. Okay, भैया देखो भैया errors आ गया. ये है error occur which is called as your dispersion. See, remedy for this, in communication we use Nyquist shaping by using a sync pulse. Am I clear भैया? Right. But remedy for this in optical communication system is we are using SMSA fibers. Okay, yesterday's class I told the same thing to you. If you want to avoid the ISI and you don't want any errors, always use single mode, because multi-mode fibers will create a problem of pulse spreading, because more modes are there, more modes will travel with different timings. One will move slower, other will move faster. Slow and faster can going to be make the pulse to be spread. इसी spread problem create करेंगे. So ISI and ISI के लिए error आ गया. हमको errors नहीं चाहिए भैया, हमारा communication system must be error free चाहिए. इसी के लिए क्या करेंगे मीन्स यू आर गोइंग टू बी यूजिंग द SMSA फाइबर है. SMSA फाइबर यूज करने के लिए एरर्स नहीं है, डिस्पर्शन भी नहीं है. ठीक है भैया. एंड दिस इज अबाउट द कॉन्सेप्ट ऑफ ISI. सो आई विल एक्सप्लेन यू अबाउट द टाइप्स ऑफ डिस्पर्शन. डियर स्टूडेंट्स थोड़ा कॉन्सेंट्रेट करो. सो टाइप्स ऑफ डिस्पर्शन वी आर हैविंग. When you talk about the types of dispersion, bhaiya, we are having two types of dispersion. One is called as intermodal dispersion. We are having the first one is called as the intermodal dispersion, and the second one is called as intramodal dispersion. It is called as intramodal dispersion. So students, I will going to be explaining you about the first dispersion, that is called as intermodal dispersion we are having. This dispersion is called as intermodal dispersion is present. I will start explaining you about the intermodal dispersion. You please copy this. The other name for intermodal dispersion is also called as the modal dispersion. Other name is, it is also called as the modal dispersion we are having. So students, please copy it भैया, copy करो भैया. I will explain you about the intermodal dispersion. I think we need to take a break. Okay. Yeah, definitely we have to take a break. So whenever we are talking about this one, so please copy this part all of you. I will explain the ISI once again for you. So take a break. It's time for you to break. So भैया 15 मिनट ब्रेक है और 10 मिनट 5 मिनट लिखने के लिए ये वाला. सो लिखने के बाद आएंगे. सो पूरा 20 मिनट भैया, 20 मिनट ब्रेक में हम आ गया. सो टेक ए ब्रेक.